Hi, this is Jonathan Gardner. This is section 5.12, example 1. So this is cyclotron motion. I've actually seen a cyclotron down there in the University of Washington back in the late 90s. There was a machine called a cyclotron, and indeed it was circular and hollow in the middle. When you actually understand how they work, it becomes somewhat of a magical machine. The fact that it's so simple and so awesome. Anyway, so the question is, what happens when you put a charged particle in a magnetic field? So we're going to have the magnetic field again with our magnetic purple. It's going to be uniform, pointing out of the page everywhere. And so we're going to have a particle, test particle, charge Q. We're going to put it in that magnetic field. And what happens? And the answer is nothing. The magnetic field does not interact with charges that aren't moving. But if this particle had an initial velocity, okay, then the force it's going to experience is going to be V cross B. Use your right hand. V cross B. It's going to point inward. Bloop. That's the force. And the effect of this is going to be a change in the direction of the velocity, not a change in the magnitude, just a change in the direction. So it's going to move a little bit and turn a little bit, if you're thinking in terms of the differentials and the tiny things that happen. So it's going to move and turn a little bit. And as it goes around, it's going to create some kind of circular path. I'll kind of draw that. So let's say it's a tight circle. And I just completely muffed that circle. But it's going to have some radius r. To use a different color for that. This circle is going to have some radius r. Okay. And in order to sustain that motion, we know that the acceleration has to equal the force. Mass times acceleration has to equal the force. So we get this simple formula. The force, QVB, that's the magnitude of the force, is going to be the change in the direction, which is just mv squared over r. Okay, and that leads us to this simple equation that the momentum P, which is mv, is equal, we're going to cancel out the q's there, so mv is equal to qbr. Okay, and the neat result of this is that you can calculate the momentum of a particle if you have a uniform magnetic field by just looking at the radius of the path it traces out. If you already know the charge, of course. If it's a particle, if it's an electron, for instance, it has a very well-defined charge. Interestingly enough, the only component of the vector that contributes to this magnetic force is the perpendicular component to the magnetic field. So if we had a situation, it's really hard to draw, but just imagine with me for a second. So the particle isn't traveling exactly perpendicular to the page, but it's kind of elevated out of the page a little bit, right? So what you do is the projection of that velocity on the perpendicular plane is the only part that really matters in calculating the force. This other component, the parallel component cross B is 0, right? And so only this component, the projection of that matters. So if it's pointing out of the page, then that projection, of course, is smaller and smaller. Okay. Because it's pointing out of the page, and so the radius becomes, well, the QBR, MV, yeah. So the amount of the radius actually decreases. Yes, it decreases, and the other part is this parallel component doesn't have any forces acting to either change its direction or to change its magnitude, and so you get the particle will trace out actually a spiral, a perfect little spiral. If I can kind of draw it at an angle here. I drew a really good spiral when I first did this video. That's a pretty good spiral. It's just going to spiral up like that. Okay, that's example 2. That's example 1. We're going to example example 2 in a moment here. So thanks for your time. Bye.